schauen, ob ich das vergesse. Good morning. I'm still missing a few, and there are too many faces actually I don't know the names. I have to do something about it. So we started to talk about information theory in general. So, as I told you already, I mean, this is really a very condensed and introduction. I don't think that you actually know information theory after that. But just what I think we need to know here is a very, very minimum. And we talked about essentially measures of uncertainty, and in a variable x, or actually in x, or actually in a probability distribution. So x can be at this point any random variable or anything which is discrete at this point, actually even finite. And we'll have to work a little harder to extend it to infinite valued variables and continuous. It's not obvious how to do it. And for discrete variables, we actually I followed essentially just mentioned it briefly, the axiomatic method of Shannon, which will essentially find the function which I called u of the variable, or actually u of the probability distribution of the variable. So he assumed that any measure of uncertainty should be a function of the probability distribution. So this is already assuming a lot. I mean, that everything is contained in a probability distribution of p, of x. And we actually wanted it to be continuous, monotonically increasing when the number of values of x is increasing. Maximum when they are uniform, minimum when they are singleton. These are not, all these are not essential. I mean, it's enough to assume it's monotonically increasing with the number of values. Let's say that x takes n values. So x takes the value x1 to xn. So this is monotonically increasing in this n, and it's maximized when it's uniform. And then he had really a very interesting assumption, which he called the branching axiom. So if I split x into two groups, not necessarily the first one, any two groups, which I call that x1 and x2, then and let's say that these two groups now will have probability p1 and p2, which are sum to 1. So p1, p2 is just 1 minus p1. And in the simplest possible form, he wanted the uncertainty of the whole distribution to be the uncertainty in this choice, p1 and p2, which is what we later call the binary choice, plus the average uncertainty. I write it like this, but because this would be more general, I can split it to more than two groups. Of course, this is very easy to extend by induction from 2 to any partition of x. What I'm going to do is the uncertainty in each of those distributions, or distribution of p of x1 or xi in this case. No, so this was an axiom. This is the branching axiom. No, and then I quoted, I didn't prove it, but I quoted a theorem, and which Shannon proved already in the early 40s, which the only continuous function that satisfies that is, there's only one function of uncertainty up to a constant factor. Oh, I'm sorry, u. Yeah, that's what I meant. Yeah. Sorry. And so what Shannon proved, that this axiom plus this technical obvious conditions like continuity in the p and monotonicity in n are enough to determine one function. So the only function, possible function u, which makes sense, is what I call the entropy. H of p, which we also write. I write it with square brackets when I put it as a functional of the distribution, and I write it in round brackets when we just call this function of the random variable. This is the notation used in many textbooks, for example, Cover and Thomas, which I highly recommend, by the way, if you want a reference book which is readable and online. You can find it very easily. It's the book of Tom Cover and Thomas, which is called Elements of Information Theory. And this is actually the best, or the most accessible, the most easy to read, comprehensive introduction to information theory. So everything that I say is in this book. Well, not everything. I would say a lot of things that are not in this book. All the introduction is there. Yes. What's your name? Remind me your name. Oded. Okay, so I never knew it. Okay. Yes.
Is U a function of the value of x or the probability?
No, so it's not a value. It's the random variable. So when we actually all the way so far, I use capital Latin letters for variables just a second, and small. So x is a value of x, and x is the whole variable. So when I say that, this is just a notation, but you have to understand it. So when I say capital X, I mean the random variable. Let's say the weight of people. Okay, this is the random variable. Can have many different values. When I say X is 60 kilograms, this is one particular value. Okay, so this is little x, small lowercase x, and we'll try to be consistent with it. This is actually a probability of the lowercase, but you also write p of big X, and this is a bit confusing. So any random variable has a probability distribution associated with it. Okay, or any not necessarily random variable in the real sense, but any variable which is any events in a sample space or whatever. I mean, as we talked about in the beginning. So this is just a notation. So this, since it's a function of the probability distribution, the probability distribution is a function, normalized set of values over the elements of X, over the values that big X, capital X can take. So it's a bit confusing, but you'll get used to it. So functionals we usually like to denote by square brackets, and functions by round brackets. This is a notation that I find very useful to avoid confusions, but it's confusing on its own. Okay, so the entropy is a function of the probability distribution, but it's a function of the random variable. So anyway, it's defined like this: the sum over all the possible values. And in this case, I'm still talking about finite number of values, the possible values of X. Sometimes it's the expectation of the logarithm of the minus, or log of 1 over p, if you want. And this is what we and everybody else call the entropy. And I really like to emphasize that entropy is uncertainty. It's not information. It's a measure of uncertainty in what I don't know. Now, of course, if I asked you, let's say 2 weeks ago, what is the natural measure of uncertainty? If you ask statisticians or most people who know something about, they'll tell you something like the variance. So the variance is indeed a measure of uncertainty of a random variable, a real random variable. It measures the width of the distribution. But it's problematic in many ways that you'll see. The variance can be small and still have uncertainty, although this is not really the case. But the variance is not as well behaved. This is much more general. First of all, we can't define variance for things which are not numbers, not real valued or anything like this. So variance is, strictly speaking, defined for random variables in the sense of real numbers. If I want to ask what is the uncertainty in words in language, or what is the uncertainty about an object which has no meaning as a real number, then either I have to embed it in real numbers, or in some vector space, actually, as people actually do with words. I mean, today we embed them in some real Euclidean space. This is what we call word-to-vec. Or we need something which is really independent of the actual properties of X. I don't care what they are. So it's really a functional of the probability distribution. Now, probability distribution, of course, are real numbers. Probabilities are real numbers between 0 and 1, normalized to 1. They live on this simplex of distribution. And for them, I can do whatever I want, but notice that everything here doesn't depend on what x is and where does it live. I don't assume anything about it. This is, by the way, one of the reasons that some people don't like these measures, because they're too general in some sense. I mean, they don't, but this is really the power of information, of measures like this, because they can be applied to anything. I mean, words, spikes, neurons, people, whatever you want. A lot of things which are not random variables in a normal sense. Okay, as long as I have distributions of it. So this is what we call the entropy. Actually, as I said, I mean, it's directly related functionally to the concept of entropy in physics, which used to be a very mysterious thing. I mean, for 100 years, people didn't quite understand what it is. So entropy in physics is also, for those of you who know what it is, it's also some measure of uncertainty, but it's a measure of uncertainty of the configuration of the physical system. So we can define it in exactly the same way, but it actually means something completely different. I mean, the relation between them is not that clear. I mean, it has to be specified. But this, so I'm going to talk about this is what we sometimes call Shannon's entropy. Shannon's entropy. So to distinguish it from the physics thermodynamics entropy, which has other meanings, which I don't, for example, the integral of heat over temperature doesn't mean anything here, or things like this. So why they're related to each other, that's a long story. I'm not going to get into it. Maybe you see it in some other courses.
But are they related? Clear? Are they related?
Sure. No, it's not. They are related because this is essentially going to count number of, or log of number of configurations, and that's something I'm going to show you. And that's how they are related. You'll get to it. Maybe even today. I am not sure. We'll see. So the entropy is going to be an important function. I mean, you already know that. And we're going to see many, many different good properties of entropy. The problem is to have too many good properties. In some sense, you can come to it from many, many different directions. And you always converge to this function somehow. But this, as I wrote it now, strictly speaking, it's defined only for, as I said, random variables which are discrete and actually have finite values. Yeah.
When do you prefer the variance over entropy in terms of entropy?
I never prefer variance over entropy. But entropy is much harder to calculate. To estimate the variance, it's much easier in general, or moments in general. Entropy is a lot more general than variance. Contains properties of higher moments. So for distributions can have, even random variables can have, third moment, fourth moment, sixth moment, whatever, a lot of higher moments which tell us a lot about the uncertainty and are not captured by the variance at all. The variance is only, strictly speaking, correct or really characterize uncertainty in a good way only for Gaussian distributions. For everything else, it's not good enough. So, but this is some sort of funny function. I mean, so we already, and I want you to develop some intuition about it and then show some properties. So we already talked about the simplest possible entropy, which is what we call the binary entropy. So binary is a probability of a binary variable. So it has essentially p and 1 minus p. So let's say 0, 1, yeah, or conflicts or whatever. Now, so a binary variable has only two values, and the only probabilities live on this simplex. So this is the simplex here is the 0, 1 interval. So it's a point in the simplex. Any point in the simplex defines the probability of a binary variable. Yeah? So, and we saw that for the binary entropy, which is going to be important on its own, it's the uncertainty in the simplest possible. So two-valued variable, 1, 0, or conflicts or whatever, yes, no, is in some sense the simplest possible variable, and it's going to be the element on which we're going to build everything. So first of all, let's understand this one. So it's essentially minus p log p minus 1 minus p log 1 minus p. This is how it's defined. And log is, unless said otherwise, I mean log to the base 2. So there is, actually, sometimes it's easier to work with ln, because especially when you take derivatives. And sometimes you actually talk in log 10 or log who knows what. So this freedom in the choice of the base of the log, as I said, is essentially just a constant factor. So this is up to this constant factor. This function is unique in the sense. So if we normalize it such that the maximum entropy of a binary variable is 1, then we measure entropy in what we call bits. So bit is the uncertainty, the maximum uncertainty of a binary variable. And of course, we know already that if you plot this function, 1 bit is the maximum uncertainty in the variable, which happens exactly when the two values are equally probable, half-half. So this is a symmetric function, of course, with respect to 1/2. And it gets the value 1 exactly from 1/2. And I said it looks a little bit like a parabola, but it's not a parabola. It's because you can see that when p goes to 0 or p goes to 1, in both cases, the slope here behaves like x log x. And x log x is singular. I mean, in terms of derivative, the derivative is infinite at 0 and 1. So this looks like a parabola, but it's not a parabola. If I put a parabola here, it will look will be under this. So the parabola with the same maximum and the same second derivative at the maximum will look like this. Something like when the slope is 1 at the end. 1 and minus 1. So this is above the parabola. Okay, it's actually above any power. So this is just to. So this is what we call the binary entropy. It's a very simple function. You can plot it yourself with MATLAB or with whatever you want, and play with it. And as you see, the maximum entropy or the maximum uncertainty in the variable is precisely at when the p equals 1 minus p, or p equals half, and this is the maximum entropy of a binary variable. We already know, it's very easy to see, that the maximum entropy of a distribution over any finite variable where x1 gets n values is exactly how much? What's the maximum? So the maximum over all distributions of over n variables is precisely log n. Okay? Because if they're all equally likely, it's just 1 over n, sum of 1 over n log 1 or minus log 1 over n, which is log n, which is just log n. Okay, so log n is the maximum entropy or the maximum uncertainty. And of course, this is very intuitive. When all the values are equally likely or equally probable, then we have the most uncertainty about the values. And of course, the entropy is 0. That's something we didn't require explicitly, but it comes out for free here. And the entropy is 0 when the value of the variable is known, which means that this is a singleton distribution of 0, 1 in this case, or it's 1 for one of the values and 0 otherwise. Okay, this is, you can easily convince yourself. And remember that we understand 0 log 0 as the limit, which is just 0. Okay. So if you're not convinced, try it yourself. Take epsilon log epsilon and take epsilon to 0. Now, okay, so this is the binary entropy. Very nice. What can it tell us? Not much. Okay, so we want to develop some properties of the entropy, and I'm not going to do it very formally. I want you to understand. So there are many properties. We already saw that if we have two independent variables, So the entropy of two variables together, x and y. So entropy is defined for any distribution. So strictly speaking, it's a strange function because it's a function out of the distribution. It can be a function of many, many variables, and the dimension of the input can vary. I mean, from 2 to infinite, in principle. So it's not, it's actually a collection of functions. For any number of variables, there is a function entropy. But it's very easy to think about it in general. Now, so agent xy is this functional of the joint distribution of x and y. That's how it's defined. Okay? Which is defined as simply thinking of x and y together as one random variable. So I simply average the log. That's really the funny thing about entropy. So usually when you think about averages, there is some random variable here. Let's say a of x something, ax, and then you average it. That's the expectation value. Here you average this particular random variable, which is minus the log of the probability.
Is it only for independent or general?
So far I wrote it in a general way. At the end of the class, I showed you that for independent it's very simple. But now I want to see what happens if they're not independent. Okay? So we can always write this. This is the kind of tricks that we do in information theory all the time. So we can write pxy in various ways. For example, I can write it px times py given x. That's always true. I can always also write it as py times px given y. Okay, so these are two natural choices here. Of course, if they are independent, then this is just px times py in both cases. Okay, so but now I don't want to assume that they're independent. So what happens? So let's pick this one. So it's the sum over x of px times the sum over y, py given x. This I can always do. I can simply break these sums. Okay, and then I have the log of px. But since the log of a product is what? It's the sum. Yeah. By now you should all know that. So this is the log of py given x. Okay? So far I didn't do anything other than breaking the probability. But now I see that this depends only on x. So I can take it out of the sum on y. Okay? So it's and I get the sum of x of px, and then I get here log of px, and actually it's minus, and then this is minus, so it's minus the sum of px, plus the sum over y of py given x, log py. It's completely trivial. But now I can look at the first sum. This and this, what is it?
Yeah.
It's just the entropy of x. So this is hx. And the second sum is something new. But so the first average is essentially the entropy of what? The entropy of y conditional on x. Okay, so this is the entropy of the variable y conditioned on the specific value of x. That's the way I want to write. Because I sum over y, but x is fixed. I did the average of it. Okay. But now I take this averaging. So essentially you get this. So this is equal to this. Minus. With a minus. No, it's not minus. No, it's not. The entropy is already with a minus. Yeah. Okay. So this is a new thing. It's the average over x of the entropy of y conditional on x. But we would like to naturally call it what? And if you just have to invent the theory. This was the entropy of X, this will be the entropy of Y conditional on X. Okay, so that's what we call it. This is the entropy of X plus the entropy of Y given X. I replace this little x by big X, by capital X, which means that I actually average over the values of X. Okay? So this is a very general formula. So the entropy of two variables, without any assumption, is this. Okay, this is nice. It's actually telling you the uncertainty in two variables is the uncertainty. Of course, in the same way exactly I can write it as the entropy of Y plus the entropy of Y conditional on X. This is exactly the same. So it's using this. Sorry, X conditional. Okay? So it's just using this, exactly the same. So the entropy, this is what the beginning of what we're going to call chain rules. So essentially we see that if we add variables, the uncertainty adds. So the uncertainty is additive in independent variables. And essentially what we did here is if they're not independent, we just condition on the previous one. So you can already get the general chain rule here. So if I have many variables, so this is the beginning of what we're going to call the chain rule of entropy. So chain rule for age of X, for entropy. So you could generalize it easily by induction if you insist. So if I have the entropy of, let's say, n variables, so what will it be? Guess yourself. So if they're independent, it's just the sum of the entropy. But if they're not independent, so try to generalize this. So it's going to be, let's say, there are many ways of writing it, because I can, essentially what I do here is factorizing the joint distribution. So how can I factorize the joint distribution? This again, it's a very important trick. I write, let's say, px1, let's say a px1 first. And then I look at x2, but now x2 is not free anymore because x1 was chosen. So I have to condition on x2. On x1, sorry. But this is now again, now I choose x3, but I already chose x1 and x2, so I have to condition on my choices. Okay, so this is p x3 given x1 and x2, and so on. Until the last one, xn given x1 to xn minus 1. So this, you can easily convince yourself that this is always true. And of course I can do it with any permutation of the values. So there are n factorial ways of writing this factorization. But let's pick one of them, doesn't matter. So if I just apply to entropy, what should it be? So the first one is going to be just hx1 as before. Second one is going to be what? Just guess, okay. It's very intuitive. It's what's left in the second variable, the uncertainty left in the second variable when I already know the first one. x1. And so on. x3, condition on x2 and x1, and so on. It's exactly the same, just reflects this product, but because of the log, the product turned into sums. That's it. So you see that this is again very intuitive. So this is for plus here. This is very intuitive in the sense that it really breaks the uncertainty of many variables into the sum of the remaining uncertainty. First one, of course, as I said, you can take any permutation. You don't have to start it. But if this is, let's say, a time series, so actually this is the order of the variables, then this is usually what we do. We first remove the uncertainty in one variable and then so on. Okay, so that's called the chain rule for entropy. If you think about it, the branching axiom is a special case of it. Because I actually split the variable into two and added another one, which is the choice between them. And then I get that the entropy sums over my choices and average. So you can think about this is some sort of generalization of the branching axiom. It directly follows from the branching axiom. Okay, so this is nice. So now we know both what entropy is and what conditional entropy. So this is already good enough to start asking interesting questions. So if you remember, let's say, take an example, just to, or application, of course, example of application. So already at this point, I can do something quite interesting with the notion of entropy. So remember, last time I asked you about the famous 20 questions game, which you all know, I hope. So I choose a number, let's say between 1 and n. If you want n to be 100, let it be 100, never mind, or 128, or whatever. And I'm allowing you to ask me questions. So originally you don't know my number. And if you think that I'm completely indifferent, which no one else is, so all the numbers are equally likely. So people actually choose numbers which are nice in some way. So it's very, very far from that. People like to choose 3, 7, 17, and so numbers like this for all sorts of funny reasons. But now mathematicians have a different prior. But let's say that you are all the numbers are equally likely. Okay. So and then I'm allowing you to ask me only binary questions, which means yes/no questions. And now I ask you, okay, without telling me how you do it, what is the minimum number of questions on average that you have to ask? Okay, so this is already becoming interesting because okay, so you can ask me, is your number 17? I'll tell you no. Okay. How much uncertainty I remove from your distribution? Not much. So now instead of 100 choices, you have 99 choices. So this is probably not a very clever question. So maybe because what was the entropy of this binary variable when I asked is it 17? So the probability was 100 to 9900. So this was in the binary entropy. It was somewhere here, okay? 100. So the entropy was the entropy of this question was low. Okay? But the chain rule or the branching axiom is telling you that the entropy that you remove is additive. So whenever you remove entropy by the question, you actually remove uncertainty from a variable. And the sum of the uncertainties that you remove is exactly going to be the uncertainty in the original variable. Okay, so what is the maximum uncertainty that you remove in a binary question? 1 bit. So this is going to be just this entropy. So if I ask questions which are what I call maximum entropy questions, which means questions which are the answer to is initially a priori before I got the answer are equally likely. So these questions are going to be the most informative questions. So for example, what is a good question in the 20 question game? Is it an even? Or is it greater than 50? Or something like this. I mean, there are many questions I can ask which are divided into 2 parts, which are equal. And actually, 100 over 2 different questions I can ask. But essentially, a good question is going to be a maximum, going to be 1 bit. Okay. What is the uncertainty? It's original uncertainty in the variable in this unknown number. Log of 100. You don't know anything. So what is the minimum number of questions on average?
Log 2, 100.
Right? Log of 100 divided by log 2 because this is the maximum I can get in one question. So this is already an interesting conclusion. I mean, this is an application that you need to think about. Is this actually a lower bound on the number of questions you should ask on average? And of course, you could be lucky and actually it's 17 and said yes, it's 17, and you think, okay. But this is going to be very unlikely in general. So on average, when I say on average, I mean if I do it many times with random randomization of my initial conditions, on average you're going to need exactly log n over log 2. Okay. So So this is some sort of a tricky type of answer because I'm talking about averages already. So that you see already something that's creeping out. Entropy describes some sort of asymptotic or large numbers. In this case, it's large number of possible games. So the 20 questions game, I'm not going to write everything on the board. So I took a number. The number of questions is log n over log 2, or log 2 of n. And this is the number of questions on average when playing the game many times.
Yes. Can you explain how do you define entropy of a question?
So the entropy of the question is actually the entropy of the answer as a random variable before getting it. So here when I ask it, is it 17, the probability of getting 1 or yes is 1 over 100. Probability of getting no is 99 over 100. So the entropy was very low. The entropy of the answer before getting. Now you can easily see, so this is easy, okay? So you see that I need log 2, so how much is log 100? It's something between 6 and 7. Okay, so in 7 questions, if it was 128, it was exactly 7, log 2. So I needed something like 7 questions. This sounds right, and sometimes it will be 6, sometimes it will be 7. That's fine. If I ask really good questions.
And the number of questions that you need to ask?
This is the minimum number of questions on average I need to ask. Now, it's a bit tricky when I say on average, because as I said, I mean, you can be lucky. And maybe your first question was right, yeah. But this is unlikely to happen. So maybe 2 questions, you can ask all sorts of random questions, but if you really want an algorithm which systematically will get the average, the minimum average, ask binary maximum, multiple maximum entropy binary questions. Okay? Now, yes?
But like it's not, it's not an average, but like if I use this algorithm, it's
Battery is gone. Sorry, yeah.
this number is not necessarily achievable, right? Because if it's not...
That's right. You already saw that with 100 I have some integer constraints. I'm not in a power of 2. So sometimes it will be 6, sometimes it will be 7. It will be something in between. Yeah. It's achievable on average when I ask many, many questions. Of course, I cannot ask 6.5 questions. I mean, I can, but I can ask sometimes get 6 and sometimes get 7. Okay? Yes?
So it's not recording now?
If someone, like, I don't have the battery, the 9-volt battery is obviously...
We can hear
You can still hear it. Yeah.
but
Now the battery is on, so I see that the light is red.
so switch it in the break.
Switch in the break. 5 minutes. Okay. Now I want to continue. This is, yes?
About the average, isn't the average supposed to be between 1 and this number? Because this is like the maximal.
No. This is the average number of questions. So again, this was the original uncertainty in my number. This is the maximum uncertainty I can get in a binary question. So this is going to be the minimum number of questions on average. And what I mean by average here is that if I repeat the game many times, it's going to converge to this number. We're going to come back to this. Essentially what we are doing here is building a code. And I'm going to come back to it in much more detail. There's a very special type of code that I just did. And you're going to understand very, very well, I promise. But this you already see. Let me give you another question which I'm not going to answer here because I'm going to get it in the exercise. You remember that how many of you know the coin problem? I mean the 12 coin problem. It's a very famous combinatorial question. I mean I'm giving it. You're given 12 coins, and I'm telling you that one of them is false. I mean, and it has a different weight. I don't even tell you if it's higher, if it's heavier or lighter than the weight of the other. I'm telling you one of them is false. Whatever. Now I'm giving you a balance. How do you call it? Muznai. Scale. Yeah. So essentially, you can put coins here and see if they're equal, or if this one is heavier or this one is heavier. Okay. So this is my measurement now. I define my measuring apparatus. In this case, it has actually 3 possible outcomes. Can be right heavier, left heavier, or equal. unlike a binary question, this has 3 possible outcomes. Now, what is the uncertainty here to start with? So again, you have to think about the random variable. So you order the coins, okay, put them in order, and call this one 1, 2, 3, 4, up to 12, okay? And now, so my random variable is essentially which one of these is for. So this has how many options, how many possibilities? The first one can be heavier or lighter. The second one can be heavier or lighter, and so on. So how many options are there? 24. Because each one of them can be either heavier or lighter. There are 2 options. Actually, you're right. If I only ask which one is flawed or false, and then you're right. But I actually want to know if it's heavier or lighter. So then my uncertainty, there are 24 different options. Remember, coin 1 is heavier, coin 1 is lighter. Coin 2 is heavier, coin 2 is lighter, and so on. So altogether, the probability space here is 24. So the uncertainty, the original uncertainty, the maximum uncertainty is how much? Log 24. Okay, just each one of those things is equally likely to start with. I don't know. So I didn't tell you anything. So all these possible options are equally likely. So the original distribution is 1 over 24 over 24 options. Okay, so the uncertainty is playing the same game for the coins, the 12 coins. It's going to be log 24. This is the maximum entropy of the maximum entropy of the initial variable. How much entropy I can remove in one measurement? Most?
Log 3.
Log 3. There were 3 options. The maximum uncertainty that I can remove is exactly when all of them are equally likely. So it's going to be log 3. So without doing anything, the algorithm is actually quite complicated. Actually, many algorithms. Actually, how to do the measurements, I didn't tell you though. But you see already that on average, you cannot do it. On average, the log 24 is close to log 27. If it was log 27, it was 3. So this is somewhere between 2 and 3 measurements, actually closer to 3. So probably 3 measurements should be enough. Okay. So this is something you can get without showing an algorithm. Now, what should be the first measurement, by the way? If I want equally likely results.
Half and half.
No, half and half is not equally likely. So you are saying, put 6 here and 6 here. No, there's a much better one. 4, 4, 4, yeah. Put 4 here, 4 here, and 4 outside. And only then you have exactly 1/3 probability that something to each one of the options.
How do you know it's the maximal entropy for a question? Maybe there is.
No, the other one, 4, 4, 4 gives me log 3.
How do you know there is no better question?
Because the number of outcome was 3. So the maximum entropy of this variable, the same question you asked before.
Yeah, so then you get.
So there is an entropy that is removed by the question, and this is the entropy of the question. Essentially, it's the entropy of X conditioned on Y, and Y in this case is the absolute question. And this is the maximum I can remove. Okay, so I can't remove more than the maximum number of options. Notice, by the way, that underneath you already see something which is going to be very important. We see something like how much uncertainty can be removed by a measurement. So this is an important question. I mean, in general, what is an optimal measurement? If you're doing experiments, you should be very careful about it. Don't ask questions which are obvious. Right? Don't ask questions when you know the answer before you start. This is a waste of time. And if you ask questions, if you're actually carrying out a measurement, we finished already, but let's see that we have an audience there. So if you have to carry a measurement, let's say I do very complicated, fMRI measurement, I don't know what. You should think very, very carefully what type of information this measurement is going to give you about what. So try to maximize this removal of uncertainty.
Can you always quantify it?
Yes, you can always quantify it. Yeah.
Even if you don't know the
Well,
number
sometimes it's very complicated.
of options?
I'm sorry?
If you don't know the number of options?
No. Sometimes, for example, it can be a continuous number. Okay. I measure the temperature in this room. So what is the entropy removed? So of course, when you actually think about it, you measure the temperature within some precision. Let's say 1 degree, half a degree, tenth of a degree, but it's not a real number. So you're giving me some precision of that. So let's say we discretize and actually care about the temperature, let's say between 10 and 30. Beyond this, 40, whatever, the maximum, and 0 and 40, whatever. So there's some scale, and there's some option.
Did you extend it to continuous variables?
Yes, we will, don't worry. You see already there's some trick here, because I need to extend the number of options to be continuum, and that's not so simple. So that before I stop, okay, so you already see, and we're going to talk about much more, that this notion of entropy has something interesting in it. I mean, it's actually giving me the ability to start asking questions about interesting things, like how much I can get in a measurement, or how much uncertainty I remove. But before the break, so essentially, what happened here is that we had two variables. We had the variable which was the original number. I mean, let's say the 20 question game, my unknown number. And we had another variable, which was the answer to my question. Actually, there are many variables. I mean, the questions are total set the same question, and I can ask them. So, and essentially what I did is I looked at the uncertainty of the original variable, let's call it x, and I asked how much was removed from the uncertainty of x when I know y. And this turned out to be the quantity I was really interested in. I mean, I wanted to remove as much as I could from the uncertainty of x by the measurement. So what is it? It's this. So this is the interesting quantity here. I mean, how much of the uncertainty in the variable x was removed by the answer to the question, which was y. Okay, so this seems to be an interesting quantity. The uncertainty removed from x when I know y. Okay, it's indeed a very interesting quantity. We're going to call it information, or mutual information. So the mutual information is defined. The mutual information between x and y is defined as the uncertainty removed from x when I know y. Okay? So this is the definition of a very important quantity which I'm going to play with a lot here, mutual information. So remember, I didn't call entropy information, I specifically call it uncertainty. Information, in any colloquial sense or in any reasonable sense, is in something about something else. There are always two variables. So I can ask you, what is the information in my page about this topic? Or what is the information in today's news in the morning about the weather in Jerusalem? Or I don't know, whatever. But it's always in something about something else. And that's why information is in a very fundamental sense, a function of two variables. How much one is telling me about the other. Okay? So this function is very, very important. And we're going to play a lot with it from now on. Now we take a break.
do you mean by bit?
No, so I actually said several times. So bit is the maximum entropy of a binary variable. So bit is binary variable it's a bit because I'm asking yes no questions. Okay, so each
What is the meaning of the type?
well, okay, I should define it more formally. Bit is the entropy of the variable which has half probability. It's the maximum entropy or the entropy of a half or an equal likely coin or whatever, equal likely yes no binary variable. So a bit is the entropy, this entropy. For half, the maximum binary entropy.
So it's like a unit for entropy?
It's a unit for entropy, that's right. And actually, okay.
It's half of the entropy or like the maximum?
No, it's the maximum value of the entropy. This is 1 bit. So 1 bit is log 2. Because when I use it with the base 2, it's just 1.
Why it's log 2?
Because the maximum entropy of a binary variable is log of the number of options. I wrote it here. It's log of n. And in this case, n is 2. So it's log 2. So bit is the uncertainty in a coin flip where the coin is unbiased.
So you use this as like a unit for when you measure the other entropy?
That's right. So this is the unit. Essentially, all it says that I'm in my entropy, I use the base log 2, the base 2.
You usually
So if I use the base 2, it will be the entropy as a unit and the unit of bits. Okay? If I use the base E, LAN, the units are called, sometimes we call them nits, natural information.
How do we pick the unit?
Or not. And when it's 10, we call it decibel or something. I don't know. That's decimal entropy.
How do you pick
When we measure entropy in thermodynamics, we actually use entirely different quantities to just relate it to a different constant. Known as the Boltzmann constant.
How do you pick the unit?
I don't think I choose.
Okay,
I choose bits. Because yes, no questions or binary variables are going to be the elements of everything that we're going to build.
Okay, but how do you choose the question? Like the type of question?
Here you saw I asked yes, no questions. I told you that I'm asking you binary questions. Yes, no question is a binary question. You tell me yes or no to my answer, to my question. So the answer was binary by definition. Just as the answer to the other question with the scale was trinary. I mean, there were 3 possible options. So I wanted to use all of them equally likely. So there the maximum entropy was log 3. It's a different unit. If I had 10 different options, or let's say you have a multiple choice exam, and you have 4 options, and a priori they're equally likely. So it's a good question, by the way. If I'm designing a multiple choice exam, I should make the choices more or less equally likely on some ignorance prior. Of course, this is not the case if you know more. If you know something, this should be less and less equally likely than because you already have information. Eventually, if you know the answer, you should be able to choose one. Okay, so you see that in the multiple choice, let's say 4 options, the maximum entropy is log 4. Okay? So the equally likely probability, where all of them are equal, this is the probability of 1 over n all the way. So all equally likely, then the maximum entropy, this is the maximum. Actually, I should prove it to you that it's the maximum entropy, but this has always the maximum entropy. This is easy to see. You see? There's always. So the maximum entropy for a binary variable is 1 bit. For a trinary variable is log 3. For a multiple choice exam is log 4. For if you measure, you have 30 options of answers, then it's log 30 and so on. So this is the maximum. And essentially what we did in this exercise here is we took the maximum uncertainty, the original, which was log number of numbers, log 100. And I divided by log 2 because this is the maximum information I can get in one question. And since the total uncertainty is additive, so the maximum, in order to remove log 100, I need enough log 2s. So that's why I divide them. This is essentially the number of questions.
Here you choose the base for 2, it's just because the trinary question,
because the question is
just
2.
easier to answer.
That's right. It's a bit confusing. But the 2 here, this could be any log.
Yeah, it could be any.
But eventually this will basically be this. So it's exactly log 2 when this is going to be 1. And it just looks like
So here is 12 coins, right? So actually it's 12 feet, right?
So this is going to be log 2 of these two numbers.
Yeah.
But I don't care which, as long as if you divide logs, I don't care about the base.
Yeah.
The base can count. So it's really the uncertainty in the original variable divided by the maximum uncertainty that I can remove in one measurement.
So make sure you ask the best question.
Yes.
If you are,
So if you want to minimize the number of questions, on average,
yeah.
you should ask the best question. Before you ask the question, this is good also for the class. Think how do you maximize the entropy of the answer?
Sorry, could you explain again why this is 3?
Because I was talking about scale, which has two sides, which can be, this one can be lighter, this can be heavier, or they can be equal.
Yeah.
So these are 3 options.
Okay.
And you want to maximize the entropy, you want to maximize the actually to the information in a second that you actually get in this measurement by maximizing the entropy of the place. So the maximizing the entropy is going to, I want to actually maximize the removal information that I get from x and y. In this case, it's going to be minimizing the uncertainty of x when I know y.
Okay.
יש לי קצת, כאילו, מאחר הקודם, שלי שונה כי בעצם רוב פעמים, כאילו, כן, הזמן שלנו כן, לא, רוב פעמים שאנחנו רוצים לעשות פרמטר אסטימיישן, אז אנחנו בעצם לא יודעים את ההתפלגות.
אנחנו מנחשים אותו, זאת אומרת, הבעיה עם פריור.
כן.
פריור זה באמת דבר שצריך או לדעת אותו by construction, אם אתה בונה את הניסוי שלך, את הזרעה שלך, אתה יכול לעשות סיבוב לדעת, או שאתה מנחש אותו באמת. זו אחת הסיבות שאנשים לא אוהבים גישות ביסיאניות, כי לפחות צריכים להמציא פריור מכל מיני סיבות, ואיך למצוא, אז אנחנו נדבר על זה, עוד מעט, איך למצוא את הפריור הכי פחות מזיק.
אבל גם בפרגמטיסטים, אתה כאילו יש לך, כאילו, תמיד יש לדעת על likelihood function. ה-likelihood function זה גם קשור כאילו אני יודע...
לא, ה-likelihood function לא תלוי בפריור. הוא זה data given from f.
אבל אני צריך לדעת מאיזה התפלגות הדאטה נלקח.
כן, זה אתה מניח שאתה יודע. לא, אתה מניח שיש לך מודל. המודל הוא P עם תטא. הבעיה זה הפריור תטא. טוב, בוא נמשיך. חם הדבר הזה. Okay, so I got many good questions during the break, but I'm not going to repeat all of them. I guess that there are questions because this is, at least for some of you, this is new and different. In some sense, you have some completely different sets of ideas, but we're going to connect everything. Once we have these tools for us, we're going to repeat and look again at many of the questions we asked so far, like estimation, decision making, and so on, and actually think about them in terms of these quantities, but I still want to develop some more, to understand more the behavior of these functions. So let's leave this. You can read what I write here, not so much. So the first thing I want to prove or to convince you is that the information is non-negative. The information cannot be negative. As I said, I define mutual information or information as the uncertainty removed in X when I know Y. And I call it the mutual information between X and Y. So first of all, the first thing that you can easily show, this is the same as the uncertainty removed from Y when I know X. Okay, this is easy. So essentially, this is a symmetric function. So the uncertainty removed from X when I know Y is the same as the uncertainty of Y when I know X. This is already a bit tricky because intuitively you may think that these are different questions. So this is already something which I'm going to prove in a second. And it shouldn't be negative, okay, because the information shouldn't be negative. It can be 0. And you see already when it will be 0, when y and x are independent. The independent age of x given y is age of x, because I don't get anything from y. So in this case, hx minus hx will have to be 0. Okay, so if they're independent, there's no information, which is perfectly intuitive. Okay, I measure one variable, measure independent variable. By the definition of independence, there's no information in the measurement of the second variable about the other. But the conditional distribution is independent of the unconditional. It's the same as the unconditional. Okay, so this is already a very simple sanity check if the whole thing makes sense. But actually, you can write it explicitly. So what is it? So I write it like this. This is sum minus sum over x, px log px. Minus, this minus actually plus sum over x and y, px times py given x. I'm sorry, py, px given y. So that's what I want here. Log of py.
So shouldn't the left term be P of y log P of x?
Sorry?
Shouldn't the left term be like delta P of y?
No, y is not there.
Yeah, but shouldn't the 6 be there?
If I sum over y, the probability of y, I get 1. I mean, I don't get anything. So when a variable doesn't appear in the sum, then the average will remove it out. I mean, it's simply an integral of the density, and that's it. It's always true. So unless there's something which depends on y there, yeah, of course, there is a sum of y and there's also p of y, but I already took it out. So that's what it is. But this I can easily write as the sum over x and y. So this was age of x, and this is minus h x given y, just by the definition of the conditional entropy, which is there. Okay? That's why I left it. Okay? So again, this information is the uncertainty removed from x when I know y. But now I can rearrange it. This is essentially pxy log of pxy divided by px and py. So this was a little bit too quickly. So essentially what there's another step here. I should write px given y as pxy over py. Okay? This is the same thing. Px given y is pxy divided by py. This is the definition of conditional entropy. And then I simply took this, because this has a minus here, I put it in the denominator here. You see? So the only thing I did here is changing the log of px given y to pxy divided by py. And now I want to combine them into one log. So I have here px. So as you said, I mean, actually, I can put it into the y. I can put py here. It doesn't. Yeah, okay. That's two steps here. One is changing this to what. I forgot what's your name? Hadas. Yeah. Okay. So what Hadas suggested essentially is writing it like this. This doesn't change anything, because I just sum over y, but there's nothing dependent on y there, so I get the marginal. So this is the same as this. Now I can put them into the same sum. But then there's a minus here, so it goes here, if I want to put it the same side. So check it yourself, this is the same thing. Okay, just open the logs. Okay? So this equals to this. So check it yourself. It's very easy. Okay? But what is this? Now that's a KL divergence. This is simply the D, our famous KL divergence between what and what? between pxy, the joint distribution, and the product of the marginals. That's what's written here. By the definition of the KL divergence. That's what it is.
The second one is not necessarily a probability.
All of them are probabilities.
Py.
Yeah, it's integrated to 1. Integrated over x and y is the integral of px times the integral of py, which is 1 times 1. What's missing?
It can be 0.
No, it cannot be 0. The integral.
No, the term can be 0.
Yeah. No, actually, well, okay, good. There is a point. First of all, they are normalized. I mean, the integral of px y was 1. Okay, I write integral actually, I mean sums. It will be integral much later. So it's the sum over x and y is 1. Okay, this is the probability. Okay? Which means that the sum, if the px is just the marginal, the sum of y of pxy is always true, and py is the other marginal. I don't know why I have to say it, but I say it anyway. Okay, these are true. Now, this cannot be 0 unless all of these are 0. And this cannot be 0 unless all of these are 0. Now, if these are zeros, then again, I have to extend my rule. Later, I told you that 0 log 0 is 0. So you can easily check. This is also simple. But if one of them is 0, then this must be 0 on top. So I extend it to 0 log 0 over 0. This is a bit more tricky, but I also defined it as 0. Because, I mean, why? Because I actually think about it as 0 log 0 minus 0 log 0. Okay, it's a bit stupid, but you shouldn't do it like this. You should actually prove that this converges to 0 if all of them like epsilon of the same scale. But this actually can be tricky, because if the denominator is going to 0 faster than the numerator, then this can be infinity. But strictly speaking, we talk about discrete numbers. Any of these cannot be 0 unless this was 0. So you always have a 0 over 0 here, and this is also 0, and these terms I don't care about. Okay, so this is here. This is fine. With this convention, I don't have your problem. Okay, and everything is normalized. Okay, so again, this convention of 0 log 0, this is absolutely, this always holds. 0 log 0 over 0, you have to be careful, because it depends how fast the numerator goes to 0 versus the numerator. So you can get all sorts of funny things. But this is our convention unless you have a problem. Okay? Because I understand this actually as a difference of 2 zeros. Okay? Fine. Now, but this is not negative, at least. This is always true. We proved it very early in the course. So this is non-negative. And it's 0 when? They're equal, which means that pxy is pxpy, which are independent, as we already know. So this will be 0 precisely when x and y are independent. Because the KL is 0 precisely when the two distributions are equal, almost everywhere. Okay. Now, okay, so this proves something quite interesting, that the information as I defined it is non-negative. This is good. Okay? And it's 0 precisely when the two variables are independent. It also proves something interesting, that age yx, or age xy, let's say, is always less than age x. Okay? Because if the difference is positive, this is always less than that. This is interesting. It looks naive, but actually it tells us that conditioning on anything reduces the entropy. So if I know something, the uncertainty, whatever it is, cannot increase. Conditioning, so this, we usually say it, conditioning reduces entropy. Or if you want, reduces uncertainty. Notice, by the way, in the last lesson I talked about the Rao-Blackwell theorem, and I told you that in some sense conditioning is also reducing variance. But this was very limited. It was limited to sufficient statistics. Actually, it's not really the variance, it was the MSE. So conditioning reduces MSE, I mean the mean square error, only when there is something, for sufficient, when the conditioning is special. Actually, conditioning can increase variance. Because, as I said, it can induce a lot of bias. And so conditioning something which is biasing your distribution can increase the MSE and actually increase variance. So unlike variance, entropy is always reduced by condition, which is really good. I mean, this is something very intuitive. You want your uncertainty not to increase if I tell you something new. Your uncertainty can only decrease. So this is an immediate consequence from the positivity of the information, of the measured information. Okay. So now we need we have actually some interesting relationship between all those quantities. The entropy of x, the entropy of y, when you have two variables, the entropy of x given y, the entropy of y given x, and the mutual information. All of them seem somehow to be related. And indeed, we actually have a nice diagram that summarizes this, which is something which allows you to remember all these relationships very easily. So imagine that my uncertainty of x is encapsulated by this circle. So the area of this circle is going to be the entropy of x. Why I can do this will become clearer later on. But let's say that y is here. So this is this area. So this is x and this is y. And this area is the entropy of y. Okay, so there are these two, they don't have to be the same, by the way. Maybe this is misleading. Let me draw it again, these different circles. So this was y, and this is y, okay? So this is the entropy of y. Just to, don't think that these two have to be equal in some way, okay? Now, there are other quantities here. So for example, this area, intuitively what should it be? Is the uncertainty removed from x when I know y. Okay, this is what's left in x. And now y, this piece disappeared. Okay, so here it should be the entropy of x given y. And of course, similarly here, it should be the entropy of y given x. Okay? So this was the uncertainty of x. When I know y, I remove this piece. This was the uncertainty of y. When I know x, I remove this piece. Okay, so what is this piece? Yeah, say it out loud. Say it. This is the IXY, of course, which is just the entropy of x minus HXY, or the entropy of y minus HYX. It's the same area. Okay, so this is an interesting Venn diagram. We call it the entropy Venn diagram. If you think about it as sets, these two variables, the intersection is the mutual information. If they're independent, they don't intersect. If they are very dependent, let's say that x is essentially almost like y, then there's a lot of mutual information between them. And if they are, it can be if they're identical. If let's say you have something like this, that y is part of x. So in that case, the mutual information is precisely the entropy of y, and so on. Yes. So independent, these two circles don't overlap because the mutual information is 0. Okay. So the mutual information is the area of the intersection of these two circles. Okay. So this is a good way to remember. By the way, what is the union? The total area. So the total area should be, if everything works, this should be the entropy of x and y. No, the total area. So the total area is hxy.
You equal to the
And now you get another expression for the mutual information. So the mutual information should be also hx plus hy, which is the sum of these two areas. But then I summed the mutual information twice. So it should be minus hxy. So this is also true, of course. And you see from this that this is completely symmetric. I mean, so the mutual information is the uncertainty in x and plus the uncertainty of y minus the joint uncertainty. This is precisely so hxy is this area. Okay, I don't know if you can see. But when I sum them, I sum this twice, and therefore the difference is precisely the mutual information. Okay? So now you got a whole list of equalities. So this was equal to this and to this, and it also equals to hx plus hy minus hxy. Okay, good. So mutual information seems to be very intuitive. I mean, it really plays the role of information in some intuitive sense, and that's why I and many others really like to replace our intuitive notion of information with this quantity from now on. But it has to be justified. I mean, what can we do with it? So we can do with it a lot of things. So one thing that mutual information obeys is when we look at Markov chains. No. I don't know why I'm going so slowly, but no. So remember that originally I wanted another way of characterizing sufficient statistics. And I want to do it through the notion of mutual information. So in sufficient statistics, I use the words that a sufficient statistics is something that captures all the information in a sample about a parameter. So if this is true, I should be able to define it through mutual information in a much more precise way. So again, remember that when we talked about sufficient statistics, I had this Markov chain. Theta goes to x, or to a sample, goes to the statistics. Okay? And I said, okay, theta is sampled from some, so there's a prior on theta, and there was a parametric family here, whatever, independent or not independent, and this was essentially the statistics, the function. So now, using the notion of mutual information, intuitively, how would you characterize S as a sufficient statistic? So just translate the words that I used before. S captures all the information about the parameter that is in the sample. So if this is true, S is sufficient for theta if what? If so let's call it X just to, do you know what I mean? Sample, whatever. So I theta X should be equal to what?
to I S of X.
I theta S of X. Okay, indeed this is true. So this is something I want to prove. I mean, if my intuition is right that this is actually a useful quantity information, then here is the test. I mean, I want to be able to characterize sufficient statistics. I mean, to quantify this notion of captures all the information about the parameter through the value of information. Okay, so is it true? So it's true, of course, but I need for this to develop a little, the notion of information a little further. So first of all, I already showed you that there's a chain rule of entropy. So uncertainty sums in some way. When I add more variables, I get more uncertainty. So the uncertainty is simply some sort of conditioned on what I already know. Now, the mutual information, so somehow you would like the mutual information to only decrease. So in general, when you have a Markov chain, let's say x, y, z, any three variables. So I'm going to prove to you now that this obeys what we call the data processing inequality, what is one version of data processing inequality. That essentially what? So this is something very important that we use all the time. In a Markov chain, we have something which we call data processing inequality, ing, yeah, inequality, or P. Or we call it actually DPI because we use it all the time. DPI is data processing inequality. Now again, you're a neuroscientist, so think, for example, about, I don't know, the auditory system. So one thing that we would like to be able to do is to take about, let's say, there's an information in the sound wave. My sound and my voice now has some information in it, hopefully, for you. Now this information reached the eardrum, and then the cochlea, and then the cochlear nucleus, and then the collicular, whatever. There are all sorts of stations there. The inferior colliculus and the thalamus, and then eventually go to the brain, to the cortex. Now, all these stations look very much like a Markov chain. I mean, each one is just connected to the previous one, and it's what we call a layered system, or there's that station. It's not precisely true, because there are all sorts of connections that go around, but roughly speaking, this is a Markov chain in our auditory processing. Now, one thing that I would like to have is that the information that I have in my voice is only decreasing when I go through. So the information in the cochlea is much higher than the information in the cortex. The interesting question is why do I need all these stations? But that's something we'll talk about later. I mean, why those stations actually help me. So this, in some sense, they remove noise, they remove irrelevant information. So already, but the first thing I want to show you in this line of argument, I just wanted to motivate it a little bit by neuroscience. Actually, there are many, many motivations like this in neuroscience, or in other things, language and many things that we actually study. So DPI is actually telling you, look, when you go to a station of processing, so X was processed here. There was some sort of processing, just like here. And Y is a function of X in some sense, depends on X, but maybe a noisy function of X. I mean, the entropy of Y can be larger than the entropy of X in a Markov chain. Because this can add noise. If I add noise to a variable, I actually increase its entropy. That's something we'll see very clearly later on when we talk about Gaussian variables. But adding noise is blurring the distribution. It's increasing the entropy. So this is something we'll see. But I'm actually saying that information cannot increase through a process. So whatever you do here, the data processing inequality is telling me that the information between X and Y is always cannot be smaller than the information between X and Z. So in other words, when I move along a chain of processes like this, I can only lose information. So this is DPI. This is what it means. Yes?
But I guess you can lose information, but then they have also less noise in some way.
Well, maybe if the processing is clever, I mean, it's actually filtering the noise, then yes, it will have less noise, but it can increase the noise. But what I'm saying that entropy can actually increase along Markov chains.
But it cannot decrease?
Information, entropy can actually decrease, of course. I can map X to one value of Y. The entropy of Y is much smaller than the entropy of X. So this can be a stupid map that takes all of the X's to one value. Let's shrink it, collapse it to one value. So the entropy of Y is going to be 0. Obviously, I cannot calculate from Z X anymore. From Y I cannot recover X in some sense, unless so the entropy can decrease or increase, can do many things. But the information can only decrease. So this is why we call it, it's actually important processing, and it's again intuitive. Information cannot be gained in these stations. I cannot learn more about x from some function of x. Then there cannot be more information in y, in z about x than there was in y about x, because y is in the middle. I mean, there's nothing in z about x that y didn't have about x. That's what it means. Okay, so how do we prove it? So to prove it, we need to extend this notion of chain rule to information. So that's actually not so hard, and it's very intuitive. So let's say that I have two variables, x and y, and I want to know what is the information that both of them together have on z. I'm proving the chain rule for information. Yeah, I know. I'm not. I don't write every word that I say on the board because this will take forever. Okay. I know. If I was really very careful, I should have done it, but I don't have the time for that. So what is this? So now I have to think about it as, so I have essentially three variables here. And I want to know, okay, together, x and y, how much they tell me about z. So how do you write it? So there are many ways. I just wrote several ways to write information. I can write it, for example, okay, let's just write it. So there is obviously a subjoint distribution of those three variables. That's what it means. I mean, I can measure all of them together. Okay? So what is P? I think about it as one variable. So this is the sum over x, y, and z of P, x, y, and z. The log of P, x, y, and z. Remember, I'm using the DKL way of writing information. This is always the best way of doing it. But now I have to divide it by what? Pxy times Pz. Okay? That's what it is. Okay? But this is what? So there are many ways of writing it, but I can write it. So essentially, it's all about the log. Yeah. The average is the average. Everything happens in the log. How I factorize it. So I can write this Pxy condition on z times Pz divided by Pxy and times Pz. Okay, this is still true. But then I can cancel this because it's the same Pz in the log. And what I get, that this log is Pxy conditioned on z divided by Pxy. But what is that? So this looks very much like a okay. So the end line. This is essentially what I want to show you is this. If this was a sequence, just like the chain rule that I had before, what your intuition is? Your intuition is the information that I have in x and y about z can be written as the information that I have in x about z plus what? Okay, so you wanted to write something like this. This should be equal. I just want to, again, to develop some intuition. Okay, so the first thing is how much x said about z. It's obviously part of the story. Okay? And then it's how much y will tell me about z, given that I already know x. This is the intuition. This should work. So this should be the information that y has about z, given that I know x. This is what I want. But what is this? I need to define it somehow. What is the mutual information between x and z, given that I know x? So what, again, using all those Venn diagrams and intuitions that I developed so far, you can easily guess it. This, if I define this to be, so this essentially, so I x z the conditional information, YZ, I'm sorry, YZ conditioned on X should be what? Should be the entropy of Y and Z conditioned on X, the entropy of Y and Z minus the entropy of Y conditioned on both Z and X. This is essentially how we define it, but I want you to see that this is a reasonable definition. So if I don't condition, I should get this expression again. It's a difference between two entropy. How much uncertainty was removed from X when I know Y? So this is how much entropy was removed from Y and Z, given that I know X. How much entropy was, sorry, yeah, Y, sorry. This is what this should be. Y given X minus HY given Z. Yeah. So this is this. This is essentially this. When I want to define conditional information, all I have to do is condition here, here, and here, and have the same condition everywhere. So essentially, if I just take this expression, the information between X and Y condition on Z should be the entropy of X condition on Z minus the entropy of X condition on Y and Z. Okay, so this is the definition in general. So everything is conditional on Z. Now, essentially what I started to do here, I didn't finish. I wanted to complete it. So essentially this is what I get. So if this is the definition of conditioning, I see that mutual information between two variables to a third variable is additive in exactly the same way. It's the mutual information that the first variable gave me, and then the mutual information that the second variable gave me when I already know X. By the way, when it will be just the sum. It will be the sum if they are conditionally independent, which means that the probability of X condition on of Y condition on X and the probability of Y condition X and Z is the same, which means that these are X and Z and this is independent. So okay, so this is my definition of conditional entropy, conditional mutual information. Mutual information. This is the definition. Sorry, there's a line here which shouldn't be here. Yeah, okay, so this is a very simple definition. We just condition everything. And it makes perfect sense. This is precisely what I want here. And of course, I can easily prove, just for the same reason, that this is a KL divergence. It's precisely the KL divergence I wrote here. So this is also non-negative. So conditional information is just like information. It's a non-negative quantity. Okay, now when I know what, so there are actually two chain rules here. So I can write this. So I can write this way. So which means I first choose Z and then choose Y. But I can also do it the other way around. I can choose first Y and then Z. Okay? So this should be equal to IYZ plus the conditional information of X on Z given Y. So these two things should be the same in general. Okay? It's just like, just like the chain rule with entropies, I could take any permutation of my variables. Here I can take, so I decided to look at this as first X and then Y, then I got this. And I can just as well decide to take first Y and then X, then I get this. So these two things should be equal, and they are indeed equal. In exactly the same way that we did before, play with the logs, and this is right. So these two are equal. But now look at the Markov chain.
Wait.
Yes.
But you didn't show how this is.
Yeah, I know. I didn't finish it. You're absolutely right. I left it essentially as an open question, as an exercise. Okay? I can do it. I just want to get to the point. I have 5 minutes. I'll come back to this. So you should be able, using this definition of conditional mutual information, to actually verify that this is this or this. These two are equal. Just from this definition. and playing with the logs. And there are many ways, you can factorize the probabilities in many ways. Essentially what I do here is factorize p, x, y, z in two ways. One is px times y and z, and the other one is py given z and x, and the other one is pxy given z. I always want to condition on z, on something. So if you condition on different variables here, you get different chain rules. So this is a very simple way of writing the chain rule of information. You have two variables here. You always condition. By the way, you can see for yourself, it's very easy that you can generalize it by induction to any number of variables. So what would be the generalization? Just as I did with entropies. So yeah, you can easily show. I mean, those who really like to play with inductions are welcome, but it's not really important. So if I have the information between a set of variables, x1 to xn, and y, so what should this be? Just extend it intuitively. So I first see x1. Okay, so it should be, I decide to see it in this order. Okay, first x1 and then x2 and then x3 and so on. So again, it should be ix1, the information between x1 and y. Okay, but this is only the first one. Now I give you another term. What is the other term? I see x2. As I see x2, it gives me more information about y, but I already know x1, so it is conditional on x1. So it should be plus ix2 y conditional on x1, okay? And so on. Plus ix3, right, and I'm conditional on x1 and x2, the same way that I did before. So whatever I already know, I condition on. And eventually, okay, all the way to the last one, ixn, y, conditional everything that I saw already. Okay, so this is the general chain rule for information. And by the way, because of the symmetry between x and y, it works in exactly the same way if I reverse it. I mean, it's different y's. And actually, later on, we'll talk about information between a series of variables here and a series of variables here. Like the input to a channel and the output of a channel, things like this. So this is important, okay? But it's very, very intuitive. And it all follows from the same sum rules that we already saw for the fact that log of product, I can break these logs in different ways. So this is the general chain rule for information. Fine, okay. But now, again, I want to go to the Markov chain, because I have only 3 minutes. So now let's look again at these two ways of writing the information between x, y, and z. So it's essentially 2 ways. Ix, y, z is either this or this. Okay, both of them are true. But now look at my Markov chain. In the Markov chain, I know that what do you think is the information between x and z given y? So in the Markov chain, again, I'll put it here. So what is ixz given y? So intuitively, what do you think? If I know y in a Markov chain, so essentially what I know in a Markov chain, the definition of a Markov chain is that along the chain, everything that z has about y on x depends on y. So essentially, the probability of x and z given y is what? They're independent. So if I know y, x and z are completely independent. So this is px given y times pz given y. This is the meaning of a Markov chain. So x and z are independent given the middle variable. Because if I fix that, that's it. You don't know what happened anymore. I mean, the only information that z has about x goes through y. Well, now if I freeze y, you don't see anything. So the information must flow through the chain. So this you can easily check, because you know that the probability distribution of a Markov chain is px times py given x times pz given y. This is what you know. This is P if X, Y, Z. Okay, this is the definition of a Markov chain. So from this, you can easily deduce this. Or in other words, the joint distribution, the condition